Next partial pressure problem. A 250 milliliter sample of oxygen is collected over water at 23 degrees Celsius and 760 torr. What volume will just the pure oxygen occupy at 23 degrees Celsius if the partial pressure of oxygen is 760 torr? So first we're collecting a sample over water, and that sample will have both oxygen and water vapor to make it up to 760 torr. And then basically they're going to dry it and remove the water. Therefore the entire partial pressure will just be from the oxygen, and they want to see what the volume will be. As we're removing water but keeping the pressure the same, you would expect the volume to go down. So first, we solve for the partial pressure of oxygen in this collection chamber. The total pressure outside your collection chamber will be equal to everything in the bottle, which is going to be your oxygen plus your water. So to find the partial pressure of oxygen, we subtract water from both sides, and we get our partial pressure of oxygen in this original collection is 739 torr. And so the water, or the oxygen sample, is taking up 250 milliliters of volume at a partial pressure of 739 torr, because the other 21.2 torr is from water vapor. Now they want to know what volume will this occupy if we change the partial pressure of oxygen from 739 torr to 760 torr. And this is going to be a Boyle's law problem, because we have an initial pressure, 739 torr, we have an initial volume, 250 milliliters, we have a final pressure, 760 torr, and they want to know what the final volume will be. So we use Boyle's law to solve for the final volume. Again, to solve for V2, we divide each side by P2. P2 divided by P2 is 1, giving us our answer of 0.243 liters, or 243 liters. And so the volume goes down 7 milliliters, which is that. If we had separated the oxygen and the water vapor would be taking up 7 milliliters. Gas density. The density of a liquid or solid was expressed in grams per milliliter. But as we said earlier, gas densities are over 1,000 times less than solids or liquids, and so we change the units to grams per liter to make it more convenient for us. The density of gases at STP is also related to the molar mass. We saw that the density at STP will equal the molar mass of a gas times the molar volume, because moles divided by moles cancels out, giving you grams per liter. And so if you're at STP, we can take the molar mass times the molar volume to get the density. Earlier we saw we could take the density times the molar volume to get the molar mass. And so this is the same three pieces of data, just rearranged in a different order. So calculate the density of chlorine at STP. When we take the molar mass of Cl2, you find that from your trusty periodic table. It's 2 times the atomic mass of chlorine times the molar volume at STP, so 1 mole of a gas takes up 22.4 liters at STP, and we get 70.9 grams per mole. That is the molar mass of chlorine. Times the molar volume gives us 3.17 grams per liter. So the density of the gas will be 3.17 grams per liter. Again, we took the molar mass of chlorine, which we find from our trusty periodic table. You take 2 chlorines because it's Cl2, so that's going to be 35.45 times 2 to give us 70.9 grams per mole. And because we're at STP, that's important. You can only use this at STP. You times it by the molar volume, 1 mole over 22.4 liters, to get 3.17 grams per liter. And this is noticeably heavier than for nitrogen or for oxygen, and so chlorine gas is dense and will sink. Gas stoichiometry. Again, with the ideal gas law, we can convert a volume of a gas into moles of a gas. At STP, it's easy. 1 mole of a gas is 22.4 liters. If you're not at STP, you'll have to use the ideal gas law to convert a volume into moles. But you can always convert a volume of a gas into moles of a gas, and then we can do stoichiometry. So we've just brought in our gases into the realm of stoichiometry. So for the following reaction, calculate the number of moles of phosphorus needed to react with 4 liters of hydrogen gas at 273 Kelvin in 1 atmosphere. If you notice, that is at STP, because 273 Kelvin is the same thing as 0 Celsius. And so we convert liters of hydrogen, and we can use our shortcut because we're at STP, so times 1 mole hydrogen divided by 22.4 liters of hydrogen. And now we do our stoichiometry, and we see that we need 1 mole of phosphorus for every 6 moles of hydrogen. And we need 0.0030 moles of phosphorus, of P4. Calculate the volume of nitrogen necessary to react with 9.0 liters of hydrogen gas at 450 Kelvin and 5 atmospheres. And again, it really doesn't matter what the temperature or the pressure is as long as they're constant, because these are all gases. And gas volumes are stoichiometric. And so it's a 3-to-1 ratio. If you need 9 liters of hydrogen, you need 3 liters of nitrogen. Because 1 liter of nitrogen has the same molecules as 1 liter of hydrogen, and they're reacting in a 3-to-1 ratio. And therefore, you need 3 liters of nitrogen. Will have 1/3 the molecules as 9 liters of hydrogen, which is what you need. And this will produce 6 liters of ammonia. Given the following reaction, 2 moles of sodium azide reacts to form sodium and nitrogen. Sodium azide is a shock-sensitive chemical, and that's why it's used in airbags, because if there's enough pressure from a strong enough accident, you initiate the chemical reaction and it basically explodes, and the nitrogen gas is what fills up the airbag. And you need an explosion because they are the absolute fastest chemical reactions, and if somebody's driving at 60 miles per hour and has an accident, you have like less than 1,000th of a second before their head smashes into the steering column. So we need a chemical reaction that's faster than that can fill that airbag up in less than that 1,000th of a second, which is where this reaction comes into. It's a very forceful reaction, which is why if you're too close to the airbag, you can easily break your nose when the airbag goes off. So, if the airbag should be filled to a pressure of 1.09 atmospheres at 22 degrees Celsius, what amount of solid sodium azide is needed to fill a bag with a volume of 45.5 liters? Well, let's do some ideal gas law. We need to know, the final answer will be grams of sodium azide. And so, what we first need to figure out is moles of nitrogen. Because if we have moles of nitrogen, then we can do stoichiometry to get moles of sodium azide and convert that into grams of sodium azide. So I need to solve for the moles of nitrogen. And the ideal gas law is PV equals nRT. And I'm solving for N. So I divide each side by RT. And that's how they get that equation in the bottom left. N equals PV divided by RT. And then we plug in chug. Again, it's the ideal gas law. Pressure must be in atmospheres, which is okay because it's already in atmospheres. Volume must be in liters, which is okay because it's already in liters. And then R is always 0.0821 liter atmospheres per mole Kelvin. And we converted 22 Celsius to 295 Kelvin by adding 273. And we have 2.05 moles of nitrogen. And now we do stoichiometry. It's a 2-to-3 ratio. You need 2 moles of sodium azide for every 3 moles of nitrogen produced. So this is kind of written on top of itself, but 2 moles of sodium azide over every 3 moles of nitrogen. Then we convert back to grams. And again, you find the molar mass of sodium azide by adding up a sodium and 3 nitrogens, and we get 88.8 grams. We need 88.8 grams of sodium azide powder in this airbag setup for it to work correctly. What volume of oxygen at 760 torr and 25 degrees Celsius is needed to react fully with 3.2 grams of propane? Well, we're going to convert grams of propane into moles of propane. And again, you find the molar mass by adding up 12 plus 12 plus 6 gives us like 30 grams. So now we have moles of propane. Now we do stoichiometry. You need 7 moles of oxygen for every 2 moles of propane. So I need 0.37 moles of oxygen. Let's double check and make sure it's a balanced reaction. 4 carbon, 12 hydrogen, 14 oxygen, 8 plus 6, 14 oxygen. It is balanced. And so this was from chapter 9. What's new in this chapter is the gas part. We need to find the volume. They're asking me what volume. And I just solved for N, so I can plug 0.37 moles in. R is always 0.0821 liter atmospheres per mole Kelvin. It's at 25 degrees Celsius. They give that to us right here. So you add 273 to get 298 Kelvin. And it's at a pressure of 760 torr, which is 1 atmosphere. And again, when you use the ideal gas law, pressure must be an atmosphere. And this will give us a volume in liters. Because if we look at our units, moles divided by moles cancels out. Atmospheres divided by atmospheres cancels out. Kelvin divided by Kelvin cancels out, leaving us liters, which is what we wanted. We get a volume in liters, 9.1 liters. What volume of hydrogen gas at 739 torr and 21 degrees Celsius is liberated if I dissolve 42.7 grams of zinc in hydrochloric acid? Again, we remember from chapter 8, zinc is more active than hydrogen, and therefore in a single displacement it will displace hydrogen, and this reaction will happen. We make sure it's balanced. 1 zinc on the left, 1 zinc on the right. 2 hydrogens on the left, 2 hydrogens on the right. 2 chlorines on the left, 2 chlorines on the right. And I convert my grams of zinc into moles of zinc. Then I do stoichiometry. It's 1 to 1. I will produce 1 mole of hydrogen for every 1 mole of zinc consumed. And so I'm going to make 0.653 moles of hydrogen, and now I solve for volume. Again, the ideal gas law is PV equals nRT. Divide both sides by V, and we get, or by P, and you get V equals nRT divided by P. We plug and chug, 0.653 moles, which you just solve for. R is always 0.0821 liter atmospheres per mole Kelvin. We took 21 Celsius and added 273 to get 294 Kelvin. And we converted 739 torr into atmospheres by timesing it by 1 atmosphere divided by 760 torr. And we get 16.2 liters of hydrogen. What the nose knows. Dogs use smell to detect many things, drugs, explosives, etc. And there's dogs that are trained to sniff for cancer. They're extremely useful in the medical field. And the newest thing dogs can sniff for is actually electronics. If somebody's trying to hide a USB drive or something, that takes the most skilled dogs to actually sniff out a specific compound that is used in the making of such electronics, which dogs can sniff out. And so it's amazing what dogs can sense that sometimes not even our own chemical instruments can sense. And that is the end of chapter 12.